what you're doing. So for this report, you need to do the results and calculation section like every other one, and you're going to do the discussion conclusion. Okay? It's a bit misleading to just have you do the discussion conclusion, because ultimately the discussion conclusion needs to tie your results and calculations back to your introduction. Okay? So while you don't have to write an introduction, you do need to kind of get a feel for what things you would have mentioned in the introduction so that you can tie those to the results in your discussion conclusion. Okay? Kind of makes sense? One of the things that isn't on that list of things for your lab report, but I do kind of expect you guys to all do, would be work on making a good title for each of your lab reports. Okay? So when it comes to this lab, thermochemistry isn't a very good title. And in fact, sorry, I must steal this from you. This title, according to the lab procedure, is an ice calorimeter determination of reaction enthalpy. Not bad, but we can do better than that. So what we want to do when we look at a title is trying to cover what's being studied and how it's being studied. So those are the two big things that need to get targeted. Okay, so what things are getting studied in this reaction or in this experiment? And your title of the procedure kind of gave you some of that information. We are looking at a reaction enthalpy. But the reaction enthalpy of what? Okay, that's kind of important, because you're not looking at the reaction enthalpy for all reactions. You're only looking at it for the reaction between magnesium and hydrochloric acid. Okay? So adding that little bit of detail is important. Okay? The next part of it is ultimately how we're going to do it. We're going to do it using an ice calorimeter, okay, or ice calorimetry. Okay? So the title that they've provided for you gets you most of the information, still missing that detail about what that reaction is. Okay? If you happen to watch the Monday, Wednesdays lecture on the EDTA one, how I would recommend approaching a title is write down all of the key words that kind of show up in your report. So what chemicals you're using, what experimental conditions you're using, what terms you're solving for. Okay? Write those down in just kind of a list, shuffle them all together, add some ats, does, wheres, and you now have a title. Okay? Should not be a complete sentence. It's supposed to summarize everything. That's why you go back and just find your keywords and try and jam them into a title. It should be pretty good. Okay? Sorry, I'm working on the okay. Questions about the title? So what we'll do now, kind of move into the introduction. Whoops, this was supposed to be stepwise. Oh well. So why are we doing this experiment? So we want to figure this out for the enthalpy. We want to figure out an enthalpy for this reaction, because if we're going to run this reaction on a different scale, it's kind of important to know how much energy is going to be released or absorbed in the course of the reaction. So if we scale this reaction up, say 1,000 times, how much energy is going to be released? Is that something that we can actually contain and trap, or is that going to be so much energy that we're then going to destroy the lab room that we're in? Okay? So getting an idea of the enthalpy, or that magnitude, should help us translate it or scale it into other experiments. So this is why that enthalpy is important. If you remember in 151 with Hess's law stuff, you can add individual reactions together to get enthalpies for unknown reactions, or reactions that you couldn't experimentally set up. So if we have enthalpies for a bunch of other reactions that we can find, we can potentially use that information and translate it into something else. So getting a list of reaction enthalpies for varying reactions is actually kind of an important thing to do. In my opinion, the last part of this is we can kind of call it just fun. Okay, why not? In the course of this reaction, we end up reacting magnesium with hydrochloric acid, and we make hydrogen gas, release some heat. So we get to play with some hydrogen gas, we play with acids, why not? Okay, it's just fun.
Sulfuric acid, isn't it?
Oh, it's sulfuric acid? Darn it. So it's sulfuric acid. I balanced that wrong. Or I put that together wrong. So make sure you account for that sulfuric acid. I'll try and adjust it as I go through this. So that's our overall why behind this. When they built the procedure, they might have had some other reasons why they built it the way they did. But ultimately, for you guys, we just want to evaluate that enthalpy. That's our why for this experiment. So now we would move into a how. Since we're looking at enthalpies, and enthalpy is ultimately a form of energy, we're going to rely fairly heavily on the first law of thermodynamics. What is the first law of thermodynamics? Nobody? Go for it.
Energy cannot be created, neither destroyed.
Okay, so energy is conserved, would be a short way to do it. So we can convert energy from one state to another, so we can't create it or destroy it, we can just shift where that energy is located. So for an individual reaction, what we're saying is that if we run the energy, we look at the energy released from a reaction, that energy must be absorbed by something else. And that when we add those two terms together, has to equal 0. So that's one of the principles we're going to look at. Those released and absorbed and it equaling 0 ultimately only works for a closed system. Why do we say a closed system? Why does it not work for any system? So all systems officially are closed within the universe. However, as an experimentalist, can we see how that energy is translated to the rest of the universe? There's a lot of places that we can't see or measure or know anything about. We don't know where that energy is going. So when we build an experiment, what we want to do is build a closed system. So instead of looking at the universe that we can't evaluate everything in, we build our own miniature universe. And we isolate that universe away from everything else. So that way, when we run this experiment, we can determine the energy released and we can determine the energy absorbed. Or we can determine one or the other. Okay? And if I know one, I can then solve for the other because I know this expression to be true. Does that make sense? So, how are we going to go about doing this? Well, the first thing we want to do is evaluate our reaction. It's a good thing I didn't put that reaction in there yet. We're going to look at the enthalpy for magnesium, metal reacting with sulfuric acid. This will give us magnesium ion, sulfate ion, which they may show pushed together, which is fine, and hydrogen gas. It's now nice and balanced as well, which is probably one of the reasons why we use sulfuric acid and not hydrochloric acid. Okay, so everything's a nice one-to-one reaction all the way through this. Excuse me. In the process of this reaction, we want to see what the enthalpy is. That could be a positive or negative value. Does anybody know what it's going to be? What does the positive value mean? It's an exothermic reaction. What does the negative value mean? Endothermic. Anybody know? Is heat released or absorbed in the course of this reaction? Just curious. It's actually released. Okay. So that heat is going to be released into the environment. This heat term is pretty much what we're looking for. That's our goal for this experiment. How can we monitor heat? We could use temperature. So we could use a thermometer. So we could put the experiment together, mix the reagents, stick a thermometer in, and see what the temperature change was. And while that's an interesting experiment to do, and one that you did in 151, I believe, you set this up where your heat released is the heat of the reaction, so that would be your heat term here, plus the heat absorbed. What absorbed the heat energy in that case? The surroundings, which we equated in 151 to being, it's not just the thermometer actually, In fact, the water, or the thermometer, I just gave away the answer. The thermometer heat term we ignore. Officially, when we look at this reaction, if we're going to add a thermometer into this, we have the heat absorbed by the thermometer as well. And that term we say is approximately equal to 0 when we did that calculation. What actually absorbed the heat released in that experiment? I don't know, that was a long time ago. It's the water. So it's the rest of the solution. So we could monitor the temperature change within the water. So we could determine our heat absorbed by saying what? That was the mass of our water times specific heat of the water times temperature change. And that, we could determine the mass of the water because we put the water in there. We also would have to add the mass of everything else, including the magnesium and the sulfuric acid. Why? Because they're still part of the system, they still increase in temperature as well. So we get a total mass. We can use the specific heat here. Officially, we'd have to use the specific heat of all of those individual species. But we decide the water is large enough, or makes up the larger percentage, that we can get away with the specific heat of just the water, and then we can monitor the change in temperature. We would then relate that back to the energy released by the reaction. Vaguely remember those calculations? At least some of you kind of remember that experiment. Okay. For that experiment to work, we needed to monitor the change in temperature. This experiment's a little bit different. We run this experiment isothermally. What does that mean? There's no temperature change. Can we solve this equation then? No. That old expression doesn't work for us. So we would have to come up with a different way to go through and solve for this. And we'll evaluate that in just a second. We're still going to use calorimetry. I don't know why I wrote standards, so we'll skip that for the moment. We'll still use calorimetry. We're going to use an isothermal calorimeter, which means the temperature does not change. So whatever temperature we start at is going to be the temperature that we end at, okay, for our calorimeter. The next thing that your lab manual mentions is the second law of thermodynamics. We talked about the second law of thermodynamics. Anybody look up what the second law of thermodynamics means? What's it referring to?
In all energy exchanges, if no energy enters or leaves the system, the potential energy of the state will always be less than that of the initial state.
What does that mean?
I don't really know, I just defined it.
Second law of thermodynamics we'll look at in chapter 17, I believe. I don't see how it's necessary to look at it or evaluate it or even discuss it as far as this experiment goes. So don't worry about the second law of thermodynamics. So we can cross that out and just kind of ignore that. So how can we set up our experiment? So now we'd end up shifting to our complications and a little bit more on what we're actually building from. So for our system, we said we can't use our change in temperature there. And we'd get rid of the thermometer because if the temperature doesn't change, are we going to see a change on our thermometer? No, so that's pretty irrelevant. Okay. So what are our complications? Our heat has to be absorbed by something without a temperature change. How can something absorb energy but not change temperature? When does that occur? At a phase transition. If we heat up water, okay, what happens is we put a pot of water on the stove. It heats up, the temperature increases from room temperature up to boiling. At boiling, what happens to the water? Changes into a gas. What happens to the temperature of the water? Never changes. So even though we're still adding energy into the reaction or into our phase transition, we don't see a temperature change. That energy is going into the energy of the phase transition. That phase transition energy is what we're going to use to determine this experiment. So our energy absorbed is equal to the energy for our phase transition. Anybody know what the energy for a phase transition would be? Do we have a temperature change? No. So that temperature unit that we had before, it's a good thing I erased it, doesn't show up in our expression. What we end up finding out is that it's going to be some enthalpy for the phase transition. What phase transition would we be looking at? We're going from ice to water, or ice solid to liquid. So we're looking at the enthalpy of fusion. That value is going to be some kilojoule or joule value per mole of ice changing phase. So we would need to somehow cancel out that mole term, because we want just the energy. So how do we cancel that mole term? We'd have to multiply it by some number of moles in that transition. Can we determine or measure moles? Not an easy thing to do. What could we measure? You go into the balance, or sorry, I keep giving away the answers. You're going into the lab and you want to measure something, particularly of a solid. What would you do? You get its weight by using a balance. Okay? Dang it, I'm working on it. So our balance is what we're going to use. We can determine the mass. Can I convert mass into moles? Yes. What would I need to convert the mass into moles? Indirectly, yes. Why would you use the periodic table?
Molar mass.
You to determine the molecular weight or the molar mass of, in this case, H2O, okay, or ice. So we would then be able to determine the moles by using our mass and dividing by the molecular weight. Dividing by? Here, let me write out the units, because I don't like it when you guys do that. Mass, molecular weight, grams, mole. Yeah, divide by the molecular weight for water. That would give us that mole value. So that's kind of cool. We figure out the mass. We're all good. We can go back through, determine the energy absorbed by the reaction. Once we know the energy absorbed, we know the energy released, and we can go all the way back to our final answer. So one thing to watch out for again, we're trying to determine the enthalpy for the reaction, not the energy released by what we tested. So if we ran this experiment, we're going to get some heat released, but that's going to be the heat released for what? The experiment that you ran, not necessarily for the reaction. So the number that you get at the end, you're going to then have to convert that further to the energy for the reaction. To do that, you'd have to determine which is your limiting reagent, magnesium or sulfuric acid. Translate that information back to your term to get an energy per mole of either sulfuric or magnesium. 1 mole of either of those is the energy for a reaction. How do we know that? We run this reaction once. How many moles of magnesium do you need? How many units of magnesium do you need? Run this reaction once. 1. Sort of makes sense? That calculation, once you actually have some numbers attached to it, will be a little bit easier to work with. In fact, a lot of the calculations we're about to get into are going to be a lot easier once you have numbers to attach to it. So it's going to be a bit difficult to get through this without that information. So that would kind of cover all the information from our, or most of the information from our introduction. The next issue we're going to run into, mass. What are we measuring the mass of? What would be changing? What's going to change mass? Only the ice is changing mass. How do we measure the mass of ice? We'll get into density, but not quite yet. Why would you have to go to density? If I want 10 grams of ice, how would you measure 10 grams of ice? What would you do? What's that? So you could look at a displacement, but as soon as you put it into the water, what temperature is the water? What's that going to do to the ice? Melt it. So now the mass that you said was 10 grams of ice is no longer 10 grams, it's 9 point something grams of ice. So how do you measure the mass of ice? It's a bit difficult. We can't measure the mass of ice directly. So what we'll do is a similar idea with the displacement. We'll look at a volume transition. We know the mass and volume are related through density. And that's where we're going to have to follow our calculations to. So, kind of stepwising through our experiment here. I'll make sure to adjust this as I see it. Oh, and as I stepwise, this is going to keep deleting itself. Remember, we're dealing with sulfuric acid. So the heat released by that reaction is going to be the delta H for our reaction. What's the heat absorbed? That heat absorbed is looking at that phase transition. I'm going from a solid to a liquid. The heat absorbed is going to be the change in mass, so how much ice melted multiplied by our heat of fusion. The heat of fusion you'll have to look up, so it's something you'll have to find either in your textbook or online. Once you've got that term, you can then go through and solve for your heat released. So how do we measure that change in the mass? Look at our experiment. There's this experiment, I know this kind of helps with it. So we look at our setup. We're going to take a large beaker, and we're going to fill that large beaker with ice and water. In the process of running this experiment, we only want the heat of our reaction. So our reaction's got a little tube running on the side there. That tube dips down into the ice-water mixture, and our reaction's going to occur in here. That's going to give off heat to our ice-water mixture. That heat will be absorbed by the ice and turn into water. What happens if there's something else in here? Say like air. The heat will also go into the air. Can we account for that? No. Which means when we set up our experiment, we have to make sure the only thing in this beaker is ice and water. So you have to be very careful with the setup. That's what one of the things that they're talking about at the very beginning, is to make sure that when you build this, no air can either sneak in from the outside or is already in there. Because if that air is there, it ruins your experiment. Next part. What happens as the ice melts? So at this point, all we've got is ice and water in here. What happens when you melt, or when you freeze ice? Let's take a water bottle, fill it up with water. Hopefully some of you guys have done this. Fill it up with water, cap it, throw it in the freezer. It expands. Ice is less dense than water. How do we know that? It floats. So what happens as the ice melts? It turns into something that's now going to change the volume. That volume we can record on the side. So we set this up so there's so much water in there that we see water pushing up the top of this pipette. As the experiment progresses, the volume in here decreases, which means what happens to the volume up here? Also going to decrease. We can monitor that change in volume. That change in volume is ultimately what your experiment is measuring. The rest of this is to help make sure you only get water in this experiment. So this is just a control to make sure you only have ice and water in here. Get rid of all the air. So that's ultimately the setup of our experiment. So when we look at the mass of ice, what we're going to do is instead monitor that change in volume. So now what we've got to do is figure out how we can relate the change in volume back to mass. Well, what is the relationship between mass and volume? Density. So the symbol for density is known as rho. Mass over volume. we could rearrange this. I think it's on the next slide. So let's see if it is indeed. Shoot, not quite yet. I didn't want to see that. So we've got the density is your mass over volume. We could rearrange this and say that our mass is equal to our volume times our density. Yes? We want to see the change in volume. So really what we're looking at is that our mass final equals our volume final times our density, and our mass initial equals our volume initial times density. Whew, it's a big mess, right? And let's just propagate that even worse. We could say our change in mass is equal to our change in volume times density. Kind of cleaned it up a little bit, right? What's the problem? What things are changing volume? What was in our experiment here? Ice and water. What happens to the volume of ice in the course of the experiment? It decreases because it's melting. What happens to the volume of water? Increases. Uh-oh. We're not getting strictly one change in volume. We're seeing two things contributing to our overall volume. Okay, well, hopefully that doesn't matter. And really, we're looking at one density. So it may be different phases, but the density of our species that are changing volume are the same, right? The density for ice and the density of water, same thing? No. Which is where this problem becomes even more complicated. So what we're going to end up doing is going back to this equation. We know our change in volume is actually due to the change in volume of our ice plus the change in volume of the water. So we would have to go through and calculate each of those changes in volumes. So do we know what those changes in volumes are? Well, we go back to our density, and so now what we'll do is say our total change in volume is our total change in mass divided by our density for ice plus our change in mass for our water by the density of water. Okay. When we measure this, what are we measuring? The change in volume of ice, change in volume of water, or our total volume? It ends up being the total volume. All we're seeing is water change, but the only reason the water is changing is because the ice is also changing. So it's ultimately the difference between those two that contributes to our volume change. Sort of, kind of following? I know, it's rough.
What's the P?
That P is technically a rho, which is density. I stick with the standard units for density, or the standard notation for density, even though other people don't. That is your symbol for density.
I just looked in for future, it says like
Yeah, I had a little curly Q on it so it doesn't look like a P. Or try to make it look less like a P. Oh, shoot, don't show that. So if we go back to our experiment, we can determine the change in volume. We know the density of ice. How would we know the density of ice? What's that? You look it up. Do we know the density of water? Yep, again, we look that up. What about these changes in mass? Ultimately, that's what we wanted anyway. We go all the way back to the very first thing. Really, we wanted the change in mass. Do we know how much the ice mass changed? No. Do we know how much the water mass changed? Still don't know that either. All we've got is a change in volume. There's no way to measure the ice or the water mass. We could try and say, okay, we measure the water first, add our ice, and let's say we did it perfectly, and we filled up perfectly. We didn't lose any mass of water in the process of this. We run the experiment. We quickly pop the top off, pull all of the ice out, reweigh the beaker. When you pull all that ice out, does it come out dry? No, it comes out wet. What is that wetness? Water. What did you just remove from the beaker? Water, which means when you go to remass it, you've lost some of that mass. How much mass did you lose? No idea. So we don't know the mass of ice or the mass of water. Ooh, that makes this. We got the change in volume, but how do we solve for those two terms? We still have two variables and only one equation. Well, what is the relationship between the change in mass of ice versus the change in mass of water? Remember, this is a closed system. What's going to happen to the mass of ice? It should decrease. Where does that mass go? To the water. So what happens to the change in mass of the water? Increases. According to the conservation, our first law of thermodynamics, conservation of energy, mass is energy. The mass does not change in the course of this reaction, which means the mass, the change in mass of the ice plus the change in mass of the water must equal 0. Why is this extra expression helpful? I now have two equations, two unknowns. What can we do? Substitute and solve. This turns into a rather beastly equation, which once again you have numbers. We can go through and kind of substitute and do those swaps around. I've found from previous experience, if I do the substitution now, 90% of the classroom just looks at me more blankly than you are now. So we'll just kind of let that slide. Okay. You should be able to do that substitution. You can put in your numbers, simplify as you want, try and go through and determine what your change of mass is. Once you have that change of mass, what can you do? Remember our initial process. If we've got the change in mass, we can now multiply by our heat of fusion, which we looked up. We now know the heat absorbed by the reaction. Again, according to the first law of thermodynamics, we know that our heat released plus our heat absorbed must equal 0. I can now solve for the heat released by the reaction, which ultimately allows me to then go through and calculate the enthalpy for the reaction. Lots of back and forth, right? Feeling sort of, kind of, maybe confident? Even a half confident? Quarter confident? Quarter. I guess I see a quarter. I can kind of help with that. So, very last thing that we need to address before we move into lab here would be the next complication. Measuring the volume. So when we put this all together, one of the things you're going to do is close it all up. You're going to put in some water such that the volume in this pipette is way up at the very tippy top. Because we don't know how much that volume is going to change. If we only fill it so that the water is up in this level, what's going to happen? Maybe in the course of the reaction it changes down to somewhere down here. Do we have any way of monitoring the volume down there? No. So what we want to do is fill it all the way up to the maximum possible. How can I get the water all the way up there? There has to be an equal pressure coming in from the other side. How do we do that? This center stock needs to have water to that level as well. That will allow us to get water all the way over to the other side. Once we're ready to start the experiment, we can now close this valve. It's now a closed system. When the volume changes in here, it has to show here. There won't be anything to equilibrate for it over here. Kind of makes sense? So we'll fill it all the way up. Problem with this system is it's not perfect. A lot of the rubber stopper, or this experiment's been done for a while, so some of the rubber stoppers have holes in them, which mean air is in them. As we set up our system, what happens to the ice? Starts to melt, which means the volume changes, which means that level drops. Okay? If there's air in here, we can't get that volume to stay exactly where we want it to begin with. So one of your very first steps of this is to put it all together and to make sure that that volume still stays relatively constant. There's very little we can do about ice melting in this. So what we're going to try and do is hope we can stabilize it to the point where it melts very, very, very slowly, so we don't see this sharp drop in the volume. It just kind of flatlines sort of downwards. Okay? If your experiment has an air leak in it, or there's air trapped in here, that volume is going to change differently, and it's going to ruin your whole experiment. So the whole first probably page of your procedure is checking and verifying that. I will help as best as I can to make sure that your experiment is set up. To do those tests, I would highly recommend that you get everything super packed in ice. So one of the things we're going to do to limit this ice melting is we will surround it with more ice. That will help thermally stabilize it and trap it, prevent it from melting too quickly within here. So to do that, we need a secondary bucket. That secondary bucket, usually the big red buckets, you'll then fill this all in with ice around it. That's going to help with this overall reaction. It's a giant mess of ice. Okay? Dang it. Once it's stabilized and you know it's working correctly, you can then get your magnesium and you can get the sulfuric acid. When do we want to mix those? Should we mix those outside of our reaction test tube or inside it? Why inside it? Because as soon as they mix, what happens? It produces heat. That heat needs to go into the ice. So what we'll do is get our stuff in there, or get one of our species in there, and then add the other one. As soon as that reaction starts, it's going to start spitting off heat into our ice. At that point, we can then start to monitor the change in volume. When do we start it? When is our initial volume? Okay, when you first put the two together, could be your initial. When's the final? Okay. What we would hope is that if we ran our experiment and we looked at the change in volume, we said time and our change in volume, in theory our volume would be at a maximum up here and it would flatline. That's a flat line. What happens? Now we add our reaction, the volume immediately drops down and then flatlines. There's no more heat being released. That's in theory. More than likely, what's your experiment look like? Pretty close to that. Where's your final volume? We got a bit of a problem with this. So the way we're going to attempt to get around that is that when we go through and plot our data, and I'll show you where to find this. So we've got our pipette reading, or our change in volume, versus our time. And what we're going to do is say, first obtain several data points to begin with. Okay? And so when you do this experiment, the procedure I don't think explains this super well. I want at least 10 data points at the beginning of your experiment, before you put in your reactants. Okay, so you need to record that. Then what you can do is add your reactants into it. We should pretty immediately see the volume change almost instantly downwards. The problem is instead of it flatlining like we had before, it just kind of slowly stops getting as much heat across. So it doesn't give us a clear final volume. So what we're going to end up doing is, after a certain amount of time, we're going to look at probably the last 5 data points and assume that our reaction is done at that point. We'll then go through and fit 2 straight lines. We'll fit a straight line to our first sequence of data points, and we'll fit a straight line to our last sequence of data points. And we're going to use this to help us determine the change in volume. Because these lines, you'll notice, aren't perfectly parallel, we don't get clean changes in volume. So what we're going to do is take two guesses at changes in volumes, or approximations. We're going to say the minimum change in volume is going to be roughly where we think the experiment stopped. And as far as the information goes, that's a guess. We're just taking a shot in the dark. We think the experiment stopped about there. What we'll then do is pick two more spots. And we now have 3 volume changes. We then go through and run all the calculations that we had before that we talked about, and we'll run those with 3 different volumes, which means we will get 3 different reaction enthalpies. We can then average those 3 reaction enthalpies, and hopefully that average will take into account that our volume measurement isn't perfect. Sort of makes sense? I know, it's a lot of different stuff to do there. So number 1, you're going to plot or get all of your data in the experiment. You're going to record volume and temperature. You're going to record that for a ridiculously long time. I want 10 clean data points at the front, regardless of what the procedure says, with recording the volume, which in theory doesn't drop. It will probably drop a little bit, but it should be fairly minimal. So that should be this initial part. Is that what you asked?
No, I said volume temperature would be volume and time.
Sorry, volume and time, yes. No temperature because the temperature didn't change. So we'll record those 10 data points. We'll then mix and just start recording for a while. I forget how long it says. I think it says 5 minutes. I would double that. I know that's a really long time to just sit there and boringly record numbers. If you don't double that time, I doubt you're going to get enough data to be able to do this accurately. So please just double that. It's not going to be that much effort. You can just record those extra times. You can chat and talk about how crappy this lab report is going to be. At that point, you're done with the experiment, and you can go through and start to process your data. As far as processing the data goes, we've got this on the next one. Whoops, maybe it's this one. I want to see a graph of your volume versus time. I don't want to see all your raw data. The graph allows me to actually interpret it. The table of data, raw data, is useless. All I can see is that, yes, you can make a table. I don't care. Give me a graph. The rest of it is going to be showing equations with no numbers. So the general format's on how you solve. Plug in numbers one time so that I can see how you got to your final enthalpy. Then you can average and show your total results. This lab, more than any other, I think has tons of equations to show tons of different manipulations on how you solve. So this one's going to be a difficult one to write up as far as the results and calculations go. Which is why I will be here to answer questions. So as far as the information there, I don't have a whole lot. I didn't really have a whole lot else I could tell you on that. As far as the experiment goes, well, do we have any questions first? I guess before I push too much further into that. So as far as the experiment goes, 8 sulfuric acid. Sulfuric acid is corrosive, which in theory you all know, right? Because it's written into your pre-lab. So please be careful with that. I don't want anybody getting burned. Magnesium It is fairly reactive, but it's not that big of a deal. It's not going to burn your hands if you pick it up. We do want to kind of limit contact with it, and we're also going to want to brush it like it says. The main reason we're going to brush it is for the main reason, or the same reason why we want to limit our contact with it. Magnesium does react with water and oxygen in the atmosphere. And what it ends up doing is generating a thin coating on it that prevents the magnesium metal itself from reacting. So what we want to do is strip that coating away so that when we put it into our reaction with sulfuric acid, it reacts evenly and consistently. To improve that even, consistent reaction ability, we can do a couple extra things. We can cut the strips into smaller pieces, which improves the surface area, so we would expect a more even reaction because we've got more surface area. We can also go through and stir. I highly recommend the stirring process. So get just a stir rod and put it in that little reaction thing and just kind of stir it around. What's an issue with that? Which can come into play with your discussion conclusion. What's that? The production of the heat, we aren't necessarily producing more heat, we're just producing more at an individual amount of time. In theory, all of that heat goes into the ice anyway. If you add a stir rod to it, what happens to the stir rod when you add it to heat? It heats up, which means your heat isn't going into the ice, it's also going into the stir rod. Can we monitor that? No. So we've lost some heat there. Another place where we could lose it. Our reaction, if you take a look at the top, it's not corked. Why would we want it corked? We want to trap the heat in the reaction. If we leave it open, heat could come out of the reaction. So we'd also lose heat. Why do we not cork it though? We generate hydrogen gas. What happens when the pressure builds up enough? We end up with a classroom full of flying corks. Okay, so we aren't going to cork anything because we want that pressure to alleviate. Yes, we do lose some temperature there. You will or some heat in that respect, and that puts error into your experiment. Okay? Ultimately, what we're trying to do is just come up with ways why your experiment failed. And in theory, hopefully, it doesn't fail. It comes out nice and perfectly, and then you can say, oh, all of these issues were things we didn't have to worry about because the number came out perfectly. Last thing about number coming out perfectly. How would you know the number came out perfectly? How do you know your experiment was good? Just something you would discuss in your results and, or sorry, your discussion conclusion. What's that? How do you know what your percent error is? How do you calculate a percent error? What's the theoretical? What are you supposed to get? Is there a way that you can figure out what you're supposed to get? How many times do you think this experiment's been done before? Probably a few, probably a million times. That data has been tabulated accurately in your textbook, so you can open up your textbook to get an accurate value for what the reaction enthalpy should be, which is going to be helpful for you because your answer should be pretty close to that value. If it's way off, what does that mean? Probably, I wouldn't actually push to a lot of error. The experiment works kind of well. If your number's way off, what probably happened more than likely? It's a calculation mistake. The experiment was probably fine. You just made a simple calculation mistake. You now have a quick way of checking and verify one way or another. Make sense? I can't remember anything else that I need to add, so we'll go ahead and call it quits there.